Now, we are interested in studying the following problem. Optimization problem. We have the following category: minimum and maximum of a function with several variables over a set S, but this time S is described by an inequality Rn such that g of x, a set of inequality. G is vectorial set, okay? Vectorial, yes. So G is function G1, Gm, and B is vector, so B1, Bm. Okay, so this time, so I would like the same purpose is to find a necessary condition for a candidate point for optimality. So let's look at suppose that we have a set like suppose I have a set described by an inequality y greater than x, for example. Okay, here is my set. Y equal x is this line. Y equal x. Y greater than x is my set. This is my set. Let's say the set G, or yes, G, or maybe let's change. Yes, G of x, G of xy, G of xy equal x minus y. So we want it to be negative, the same size. That is, yes, which is equivalent to say that y is greater than x. So this is my set. Okay, this is the set described by g less than 0. So yes, so depending, so so how can so we have this two situations. If I am inside the set, an interior, so locally everything will work like an unconstrained problem. Okay, an unconstrained problem. If I am on the equalities part, then it will work also like a problem with constrained optimization with equality constants. But our purpose is to find a way to consider both situations simultaneously. Okay, so this is our purpose. Now, we know that the idea of optimization, so it comes by comparison to characterize the candidate points. So when I compare values of f, so there is I cannot globally cannot compare in all directions, particularly when I am on the boundary here. So if I use any direction, I will leave my set. Okay, if I am inside, yes, I can use comparison in any direction. But if I am here, it will not work. So a way to include both situations, the suitable way is more considering curves like we did for when we had equality constraints. So I would consider all. So I will say that this is a candidate point if I can check for any curve passing through x, starting, or okay, so x star, and remaining inside this my set, constraint set. I can make the comparison. Okay, so we would say we will then compare. So let's consider the set of all curves. Okay, so we will consider all the set of curves xt belonging to the set of all curves, so xt t from 0 to a, in interval 0a closed, defined, okay, that assign xt. X is C1 function, okay, C1 function of 0a. What else? We need also, so with an e positive, okay, and x starting that x0 is my x star, the point that we are suspecting that it is a candidate for optimality. Okay, so T belonging. So this is so when comparing, I will say I will have so fixed T along this curve, okay, will be less than, yes, and yes, I want these curves included, all this set of curves is included, no, or just not functions like no, not functions, but the set of xt here, I need to specify that it remains in my set S, okay, of contents. So when I compare, I take functions like that, the values taken by f remain less than f at x star, okay, which is f at x0. Again, the same reasoning, ht, h0, okay, for any t belong to 0a. Then that is ht minus h0, okay, less than 0. If you divide by t, t is positive, t minus 0, then taking limit, the limit exists, my function is differentiable, limit of the ratio, okay, the limit as t approaches 0 plus, okay, will give me h prime at 0 is negative, okay. So we will deduce this condition. Now let us express what is h prime. H prime t is the derivative with respect of t of the composite function. Okay, general formula says it's f prime at xt, okay, x prime t. Now at t equals 0, so we will have then those quantities. We will have so f prime at x star dot x prime at 0, okay, is negative. So yes, we have then, if we have a candidate, then necessarily we will have a condition like that, where we see that the tangent vector at 0 to these curves appears. So let's just gather all the set of these vectors. Let's call this these set of vectors. So we want to find a way to express our necessary condition with simple tools. So if we consider all the tangent vectors for such curves where t, okay, xt is continuous, belongs to S, x, so the function belongs to C1 0a, we for some a positive, and starting from at instance 0 from x star. Okay, so we would like to characterize this set of okay, independently of the curve each time, considering parameters curves like that. Okay, so we have then, we can characterize, we have a result. So the first one, here is the result. Let's say call it proposition. So we establish that we can check then if x star is at the interior, okay, S0, which is the set if my function is continuous, okay, it will be something like that, okay. Then T is exactly the set of all the space, okay, it's the space entirely. The second now situation where we can characterize, identify the set of tangent vectors is when we consider regular points. Okay, regular points for x star is the set. So let's give exactly our set. What is our set? Okay, so let's identify the set of tangent vectors. Okay, so here it is. It will be equal, t will be equal to the set of y in Rn, such that the derivative I at x star, okay, y less than 0 for I belonging to I x star. The set of index I of x star, okay, is the set of all I where we have gi equal bi. So we say that the consonant is active where we have equality. Okay, uh, active constants. Okay, so and we want, okay, those vectors to be linearly independent. So if we regroup the in vector g, the GER1, so suppose this set is E1, let's say EP, okay, then GE1, GE2, GEP, this new function is taken to the P functions. The rank of G, G prime at X star is equal to P. Okay. In this situation, so when we have if we have this condition, we can identify our set as this as characterized like that, which is much better than manipulating curves xt that we don't know the equations. It's not easy. Okay, so here it is related directly to the derivative vector of the content. That's all. Okay. Okay, so this is the main result. Okay, and we call it con, but more practically so we use the translation of this vector and we denote it as cx star. It's more practical to visualize to graph at x0 x star. So it will be the set of x in Rn. Okay, the x are x star plus y, so y will be x minus x star. Okay, gi prime x star, y minus x minus x star. Okay, so yes, you can write it like that. I with I belonging to x star, I x star, or we can also write it differently using the g, the x is in Rn, using the capital G, G prime at x star dot x minus x star. Okay, I belonging to I of x star. So this is what how we can characterize, and this is, we call it con of feasible directions. Okay, so this is what we wanted to to introduce here. This new tool is necessarily it will facilitate for us to characterize the candidate point for optimality. So let's just practice and see how we can, through some examples, how we can graph the sets. An example. So suppose that we have a set S defined of constraints defined by the set of xy in R2 described by G1 xy equal x2 plus y2 minus 1 negative, and G2 of xy equal x minus y negative. Okay, so we have this. So here you see that your function g is formed by two functions g1 and g2, and we can consider b as the vector 0, 0. Okay, So it's yes, and we will consider a particular point of the set and look for the cone of visible direction at this point. So first, let's graph our set. If I want to graph the set, so I see the first condition describes the disk, unit disk. Okay, here it is. Okay, and so this is my unit disk, and y greater than x, so this is my line, y equal x. Okay, and the region, so finally the region is this one. The common region of the two is formed by this half disk. Okay, so this is the set S. This is our set S. Okay, now let's consider what is, for example, the cone of visible direction of a point inside the set, for example. Inside the set, I can consider the point minus 1 over 2, 1 over 2, for example. Yes, minus 1 over 2, 1 over 2. So directly, since it is interior, I know that the cone at minus 1 over 2, 1 over 2 will be the whole plane. Okay, we don't know to write details. Now, what about the point with coordinates minus 1 over 2, minus 1 over 2? Now, okay, what is C? What is C at minus 1 over 2, minus 1 over 2? So the point is somewhere here, okay? Somewhere here. So it is at the boundary, it is on the line. Okay, so I see that I am in the situation where I have one content that is active. Okay, it's not because inside the disk I have strict inequality, so only we have only G2, only G2 is active. Okay, active. Okay, so C. So from so my capital G that I will consider will be G2 only, and from the definition, the characterization we established here, it will be given by the set of so C will be the set of all xy such that G prime at minus 1 over 2 minus 1 over 2 the vector, so x minus half plus half, y plus 1 over 2. Okay, the only active constraint, okay, is negative. Okay, so what is G prime here? So I can compute G prime, which will be G prime at xy. Okay, so we know how to compute the derivative of the function of two variables G2. G2 we said it's x minus y, x minus y, so G prime, so I don't need to just to add here. Let's do the calculation directly. Okay, continue here. So it will be the set of xy. G prime then is my derivative with respect of x, and minus 1, then the vector x plus 1 over 2, y plus 1 over 2, negative. Okay, so okay, negative. Now let's write a thing, do the calculation. So x plus 1 over 2 minus y and minus 1 over 2 negative. Okay, which is the set exactly? Xy such that x is less than y is greater than. So at so we can graph here our set. Yes, let's visualize our set here. So here is my line, y equal x, and the cone is formed by the point above this line. So we will have this set. So including the line and yes, this region. Okay, so this is my set, my cone. So this is the cone, C at minus 1 over 2, minus 1 over 2. Okay, this is all the directions we will use. Okay, for yes, we said for minus 1 over 2, 1 over 2. So it was this point. So here the cone at minus 1 over 2, the point minus 1 over 2, minus 1 over 2. Here it was an interior point, so we had, for this one, we have minus 1 over 2 and 1 over 2. It was this one. So the solution, all the possible points were this one. Okay, so the whole plane. Okay, we need to consider the whole plane. Okay, so this is C. What about another situation where we have, let's consider, for example, the corner. This corner is common both the two continents. Let's say, okay, so it's the point 1 square root of 2 square root of 2. Okay, so let's do it here. Sorry. So the other point we will consider here is the point C 1 square root of 2, 1 square root of 2. Okay, so both are this time are active. The two continents are active. So the G prime, the G, okay, for this situation is formed by G1 and G2. Okay, so it will be G1 prime, okay, at G1 prime at 1 square root of 2, 1 square root of 2, and x minus 1 square root of 2, y minus 1 square root of 2, negative, and G2 prime at 1 square root of 2, 1 square root of 2, x minus 1 square root of 2, y minus 1 square root of 2, negative. Both, okay? So let's write in detail what is happening here. The derivative of G prime, so it's 2x, 2y, so it's 2 times, so it will be 2 square root of 2, 2 square root of 2, x minus 1, y minus 1 square root of 2, negative, and here we said it's 1 and minus 1, so 1 minus 1, and x minus 1 square root of 2, y minus, okay, negative. Then, so if we write things, we simplify by 2 square roots, so we will get the set of point x, y, such that x minus 1 square root of 2 plus y minus 1 square root of 2 negative. And we have x minus 1 square root of 2 plus y minus 1, no, minus, sorry, it will be minus y and plus 1 square root of 2 negative. Finally, it's the intersection of these two regions. Look, xy, so you have x or y less than minus x minus 2 over square root of 2, and y greater than x. Okay, so we have we can graph this easily. So we will have something like that. We have the first line, y equal x always. So this one easy to write, to graph. So we will need to have this region or both this line and to intersect with this region. So for this region, for x equals 0, let's say, or for x equal 1, x equals 0, so my point is here. Let's say my point is here. My point 1 over square root of 2, 1 square root of 2. So 1 square root, so it is part of the line, and another point x equals 0, I will have minus 2 times this distance. minus 2 times. For x equals 0, the y is x equals 0 minus 2 over so I'm just trying to guess to find the value to graph the line. Okay, y so it will be plus. Yes, here I did mistake when I move it to the, that's why it was harder for me. So 2 over 1 4, that's why it's 1 and something. So x equals 0, we will have 1 and something. Okay, so let's say this is my line. Okay, this line, suppose that we have this line. This is, let's say it's the line y equal minus x plus 2 over square root of 2, and we want it to be, to consider the points that are less below, okay, that are below, so the points that satisfy this. Okay, so the common point, the common region is this one. So my set C is here. C at 1 over square root of 2, 1 over square root of 2 is here. This is my the common region. This is and the shape, you see, it's like a cone. Okay, you see, this is my I can use another color if you want. And yes, well, this one clearer. So we will have something like that here, the common part. Okay, this is C, the cone. So yes, so we will work then. So it's enough to to test, to work on those codes, okay, to establish the necessary conditions. We will see later. Next, okay. So this is the motivation behind of these the sets, okay, because we needed to compare values are taken by f on close to a particular point, but the practical way is to introduce curves. And now these curves, so naturally we had an inequality, but we wanted to have something more practical to avoid passing through this unknown function x to describe all. So we needed only the directions to characterize the set of directions, and we found a characterization when we have regular points. Okay, so this is the main